Today we finish the first part of this course about special techniques for estimating the causal effects based on cross-sectional and panel data. Just a reminder, that's what I'm talking about every class, that our primary goal is to estimate the causal effects. Or last time we also called them treatment effects. So you make some action or you introduce some government program or probably impose some policy in the firm, and then we want to know what is the effect, what is the causal effect of this action. We know we have been talking about this since the first class of econometrics, that the major obstacle, major barrier for this is that we have an observational data. And in the observational data, we don't have exogenous treatment, exogenous in a sense that it is somehow correlated with other variables. Sometimes these variables are not observed. And that's why if we are not able to conduct a randomized control experiment, the observational data is very poor for estimating the causal effects. So far in this course, we have discussed several techniques to deal with this potential endogeneity. So one was about instrumental variables. You simply need to find some variable that is correlated with your problematic variable of interest, with your treatment, but which is not correlated with some other variables that influence the outcome. Another one was using the panel data when you have some repetitive observations through time. You can include entity fixed effects, time fixed effects, and you can potentially control for the variables that are not changing over time and that are not changing across the entities. So today we introduce two more techniques that are somehow based on the idea of randomized control experiment that we have discussed last lecture. So one is called difference in differences, or in short diff and diff, and the other one is RDD, or regression discontinuity design. These two techniques are very popular nowadays, and many authors are trying to use them when they want to evaluate the effect of some policy. So we start with the definition of what can be called a quasi-experiment. So it is not a usual experiment when you conduct a randomized control experiment, when you randomly assign your entities or people into treatment and control group. Well, we know that it is not always possible to do, but sometimes if the circumstances are such that you can believe that randomness is introduced with the help of the circumstances, we can use this setting as a quasi-experiment. So what are these circumstances? So for example, there is unexpected change in some legal institutions, location, timing of policy or program implementation. So what does this mean? It means that this change must be completely unexpected by those who are treated and who are not treated. It's not like, there is a long introduction by the government that, well, dear people, we are going to increase the pension age, or we are going to reduce taxes. If it is already expected, people, firms will adjust in advance. If there is an abrupt and unexpected change in the policy, and some units are affected by this policy and some units are not affected by this policy, then if you of course, if you argue and if you logically can explain that this change has not been expected, then you can think about this as random. Natural randomness occurs because of some natural disasters or probably just by chance. So birth dates. So when the child is born is more or less random. I mean, so it is not very simple to predict that the person is going to be born on the exact date. There is always some randomness here. Rainfall, the level of rainfall. Some other factors like flood, maybe hurricanes, maybe earthquakes. They can be unrelated to the causal effect, and therefore we can also use such settings as potentially random, and the treatment can be also assigned as random. So we call such experiments quasi-experiments because we as researchers do not influence the distribution of treatment, but the treatment is distributed randomly because of the nature or because of the governmental policy. So quasi-experiments or natural experiments. Well, at the moment I thought that one of the recent examples of such unexpected changes might be this partial mobilization. Because, well, to some extent, in the given group of people, there was a randomness, right? So who is gonna be recruited and who is not. So we know the total number of people who are gonna be recruited, but within the target group, we don't know who is gonna be treated and who is not gonna be treated. So this, like treatment, so probably this treatment, well, we can think about the treatment as losing job, for example. So because of being mobilized, you lose job. And then because of this, and probably you lose some experience. And then we can use this treatment to estimate the effect of something. Well, it's up to you. So I'm giving you this nice scientific idea how you can use observational data on the settings that are surrounding us as a natural experiment. Well, in a natural experiment, there must be always a control group. So it is not like the total population is affected by the treatment. No. If, like, I don't know, if something changes for the whole country, it is not a suitable setting. So you need to have exactly the case as it is an experiment when you have two groups. One is affected by treatment, another one is not. And yes, so one must be affected by the policy change, another one should not be affected by the policy change. And yeah, these groups in natural experiments arise from the policy changes, as I explained you. So to some extent, it is random who is recruited and who is not recruited. And then this affects some variable which you can think of as a treatment, like losing job, or maybe relocation of a person, maybe something else, like some military training, whatever. And then you can come up with the idea what is the outcome variable that you want to study, the causal effect of being recruited on something. Well, that's a perfect setting for the natural experiment and conducting some scientific research. To the extent that you have an access to the data. So that's the most important thing. So if you want to use the setting, you really need to know, you really need to have an access to all the data about people who are recruited and who are not recruited. Okay, so this is the initial thing, and when you read some papers in econometrics, in applied econometrics, you usually have a long explanation about the empirical setting, some institutional explanation probably, that is done in order to provide a reader with the understanding of this setting. And so the authors are trying to explain why you can think about this treatment, about this variable as being random. This is a very important step in order to proceed. You cannot simply use these techniques anywhere with any data. No, you really need to use this setting in the suitable, you really need to use these techniques in a suitable setting when you're able to argue that the treatment has been distributed randomly, or as if randomly. Well, the first type of estimator is difference in differences estimator. And the idea is the following. So in the natural experiment, we do not have a control over the randomization. So the randomization occurs without us. We are simply looking around and searching for the source of this exogenous change in the treatment. And the problem is that since we are not able to introduce this randomization by ourselves, control and treatment group can be different. So we discussed last time that if you are conducting the true experiment, it is very nice when you choose the comparable participants in the treatment and control group. So all the other variables like age, income, gender, something else, so the distribution of these variables in the treatment and control group must not be different. But if we are looking for these natural experiments, sometimes these differences might be present. And the idea of this difference in differences estimator is to compare the change in the outcomes pre and post treatment between these two groups, between control and treatment group. So there is going to be some change before and after experiment for the treatment group. There is going to be some change before and after for the control group. If you remember, last time we just compared the outcome for the control group, for the treatment group, minus the outcome for the control group. That was our differences estimator. But now, since there are some changes, some trends, we need to introduce this difference in differences. So it improves a difference estimator that we have discussed last time, because we compare the changes. We compare the change in the treatment sample with the change in the control sample. And it gives us, in such cases of natural experiments, the better and more reliable outcome. Because a simple difference estimator is not applicable here. So let's see how this estimator is constructed. It is very simple and very logical. You can estimate it with like 4 steps. So first of all, we need to introduce several important variables. So here, all statistics. So y bar is the sample average. So what is the most important sample average of what? So y bar treatment for the treated group before the policy change or before the treatment has been applied. So the sample average in the treatment group before the experiment. So in this similar way, we introduce treatment after. So the sample average in the treatment group after the experiment. And you can think, like usually people do, the following. They compare this y bar after and y bar before, and they immediately tell that, well, this is the effect of treatment. But it is not true, because before and after, so this effect or this difference can occur because of two things: because of the treatment and because of some natural change. I mean, just that change that would occur even without treatment. So how do we know what would occur without the treatment? We need to look at the control group. So we also introduce the sample average for the control group before the experiment and sample average in the control group after the experiment. So then this difference, as I said, is the average change over the period for the treatment group before and after the experiment. Right? So as I said, usually people take this difference as the causal effect, which is not correct. We need to look at the change in the control group as well. So what was the change over the period for the control group before and after the experiment? And since the control group is not affected by the treatment, this change can be thought as, well, as some natural change. If I'm not given a treatment to a person, to a firm, then this change would occur even without this treatment. Therefore, this change includes two components. So this component and the effect of treatment. And the difference in differences estimator is simply the difference between these two things. So I forgot to put this in parentheses. It must be also in parentheses. So one difference minus the other difference. That is why this estimator is called difference in differences, because you have one difference, you have the other difference, and then you take the difference of two. So you see that this is very simple. You just need to compute four numbers, four averages, and then proceed in a logical way. This is an illustration that gives us a very nice sense of what is going on. Look, we have before treatment time and after treatment time moment. So this is the, what we can call this a trend. This is a change in the outcome variable for the control group. You see that since this is a control group, it is not affected by the treatment, and there is some change has occurred from 20 to, let's say, 30. We also look at the treatment group, and treatment group, the outcome for the treatment group has changed from 40 to 80. But this change from 40 to 80 is not attributed fully to the treatment, because first of all we need to think, kind of like, if you remember last lecture, we posed the problem that we are not able to observe the same unit, the same person or the same firm in two states, treated and not treated. And that's why we needed this control group to think about the control group as the state of not treated person. But now this blue line is our projection, like we are building a parallel world. If the treatment would not be implemented, then this group would end up here. Why do we know this? Well, because the control group ended up here. So for the control group, the change was plus 10 units for the outcome. So then we logically claim that for the treatment group, if the treatment would not be applied, the outcome would be 50. But in reality, we see that after the treatment, they ended up at 80. So 80 minus 50 is exactly the causal effect. Not 80 minus 40, but 80 minus 50. And this 10 is a natural change. If no intervention, if no treatment was applied. So here is the explanation. So for the before the policy change or before some natural disaster, so before the treatment, so the sample average for treated group was 40, for not treated group was 20. Okay, so after the experiment, the control group raises to 30, so plus 10, and we can think of this change as a natural increase without a treatment. So therefore, we would expect that this 40 would also increase by 10 to 50. And but we observe that the difference was 40. And part of this difference occurred naturally. So therefore, the treatment effect is 40 minus 10, which is 30. Very simple, very logical, very elegant way of estimation of this causal effect. The only important thing that, as I said, for both control and treatment group, the treatment must be introduced unexpectedly. So the treatment must be truly random for them. Otherwise, if, for example, the treatment somehow was based on the characteristics of this treatment group, we will, as usual, have the problem of endogeneity, the correlation between X, in this case treatment, and error term, biased estimate, and all those unpleasant results. You can look at this and tell me, well, for sample averages, some differences. Maybe knowing the OLS, it is not very optimal to do these things. I would agree, and therefore, in many cases, people do the same with the help of OLS. So we can write difference in differences estimator with the help of OLS regression. We need to introduce two variables. So one variable, let's denote this as dt, is a dummy variable which is 0 in pre-treatment period and 1 after the treatment period. So on this picture, d is going to be 0 here and d is going to be 1 here. X is a treatment variable and x is equals 1 for those who receive the treatment and 0 for those who do not receive the treatment. So x is 0 for control group, x is 1 for the treatment group. And the simplest form of this model is the following. So you know about the differences estimator. So now we introduce this difference in differences estimator in the same way. So one variable is our time dummy, another variable is our treatment dummy, and then we also need to introduce the interaction. So don't forget that we studied this interaction term last semester when we spoke about nonlinearity. And now you can think how this is related to the previous discussion. So on the exercise session, you will also have a chance to do this manually and to closely study how these betas are related to those y bars from this slide, because they must be somehow related, right? So look, if we have dt0 and xi0, what is going to be the sample average? It's beta 0. And what is the group for which d and x are 0? This is control group before the treatment occurred in pre-treatment period. So therefore, the sample average for the control group is beta 0 hat, the estimate of beta 0. And population average is beta 0. After the treatment, the expected value for the control group is going to be beta 0 plus beta 1, because x is 0, d is 1, so then we will have this. Now, if we have the treatment group before, then x is 1 and d is 0. So it's beta 0 plus beta 2 here. What is the sample, what is the expected value for the treated group after? This is the sum of all betas. Beta 1, beta 0, beta 2, beta 3. So all these dummy variables are 1s. What's the difference after minus before? It's beta 1 plus beta 3. So now the last line is the difference between treatment and control group here. So treatment minus control, before it's B2, so that vertical distance between the lines on the picture before. And after it's B2 plus B3, you see that this difference contains two parts, B2 and beta 2 and beta 3. So this vertical distance consists of this distance as the initial distance and this distance as the treatment effect. So therefore, the treatment effect is here, it's beta 3. So it's a coefficient on the interaction term. So this, we need to estimate this OLS regression, and the OLS estimate of beta 3 is going to be difference in differences estimator. And as you can see, since we are able to formulate this problem in the form of OLS, then we can apply all the things that we have been discussing before. Multiple regression, control variables, and all the other techniques that are applicable to OLS. Why? Because now it is simple. Just add W's and you are done. And I want to show you an example. This is the most popular classical example of difference and differences that you are able to find in almost every textbook of econometrics. And if you will continue your studies and if you would ever encounter econometrics, I believe, I swear that you will see this example once again. This is an example based on Krueger paper, minimum wages and employment. So what is this paper about in the nutshell? So these two authors investigated the impact of New Jersey's 92 increase of the minimum hourly wage from $425 to $505. Well, the usual economics says that if the minimum wage increases, we can expect decrease in employment and increase in prices. And as usual, applied econometrics want to test some economic theories with the empirical setting. So they selected a sample of fast food restaurants because these firms are the major employees of of the minimum wage workers in the US. So it is not reasonable to take some like banking sector or oil producers, because for them it doesn't matter what is the minimum wage. But they really wanted to find out such firms that are affected by this decision, by this policy change of the government. And the firms are those firms that are forced to implement this minimum wage. So they also selected a control group. They needed a control group because, well, in the whole state of New Jersey, the minimum wage has been changed. And as a control group, they took the restaurants, the fast food restaurants from the nearby state of Pennsylvania. So more specifically, they took the restaurants near the border between two states. Why do they do so? Because if you live near the border between two states, then probably all the other characteristics, like social economic characteristics, the characteristics of people, they might be more or less different. They might be more or less similar, and you don't need to bother with potential endogeneity of this treatment. So in Pennsylvania, the minimum wage was constant at $4.25, so the same initial level, and during the whole year it was the same. So therefore, yeah, these restaurants that are just across the border, they were taken as a control group. And they collected the data over the period of February. So this is a pre-treatment period from February 15 to April 3rd, and then the after-treatment period from May 11th to December 31st. So here is a table with the sample averages. So let's see what is here. So this is a treated sample of New Jersey restaurants. So before, and the numbers are the average number of workers in the restaurant. So 20.44 is the sample average number of workers in the restaurant in New Jersey before the minimum wage increase. And look what we see. After the minimum wage increase, the average number of workers was 2103. So overall, this difference is 0.59. If you don't look at the right side of this table, if you look only at this column, you can believe that, well, the causal effect of this increase in minimum wage is positive. And it is somehow surprising, right? Because, well, you increase the minimum wage and the employment has also increased. But the theory predicts that when wages increase, firms reduce the employment. And this is not correct to look at this number, because this number contains two things. So one thing, so you always need to think about the following. Well, maybe over the time there was, well, something increase in needs of these restaurants for people, and that's why it is not because of wages, but it is because of some other factors. This positive increase has occurred. So therefore, we need to look what has happened with the control group. The control group which was not affected by this decision. And in the control group, we see a very surprising result. Before the minimum wage was increased in the nearby state, the employment was, the average number of workers was 23.33. After this change in the treatment group, the employment and control group decreased to 2117. So it is minus 216. And we can take this difference as the difference that would occur without the treatment. And therefore, the difference in differences estimate is 275. So this is our estimate of a causal effect of the increase in minimum wage. So it is even more surprising regarding the prediction from the economic theory. So increase in minimum wage led to increase in employment by, so if you compare this with the baseline, it's almost 30%. So here is an explanation that I said, yeah, 275 is the difference in differences estimate of this impact. We don't see any standard errors here. We are not able to proceed with some statistical inference. We are simply looking at the numbers right now. So, of course, you might argue that, well, is this effect is significant? And I would say, well, let's estimate this with the help of OLS, and let's see. So here are the OLS estimates of the regression model for difference and differences. And we see that, well, this causal effect estimate is not statistically significant. But don't forget about control variables. So we have not included the control variables, though the authors did, of course. They estimated another specification of the model. And of course, there might be the bias estimate here if we don't include the control variables. But for our class, it is enough, because I wanted just to illustrate you what is the logic of difference and differences estimator. The logic is very simple. And observing these coefficients, what can we see? Look, the intercept 23, 33. What does it coincide with? It coincides with exactly before treatment control, with the sample average of a control group before the treatment, 23, 33. Look, when we look at this table, so the difference for the control group after and before must be corresponding with beta 1. So let's see, for the control group, difference between after and before, it's minus 216. So let's see on the OLS estimates. Yeah, it's 216, exactly here. For the state, it is what? It is the difference before between treated and control group, 2989 here. And finally, the difference in differences estimate is the coefficient estimate on the interaction term. Well, based on the discussions that we usually do, this is a baseline model. So, and then you saturate this baseline model with the control variables. You can include some social economic characteristics of these states, of the restaurants, something else, in order to improve the estimate of this difference in differences estimator, in order to improve potential bias and solve some other potential problems. So we can extend it with additional regressors, and these variables can be some individual characteristics before the experiment or some control variables. And then your OLS regression for difference in differences estimate is going to be looking at this formula, and again, definitive estimate is the estimate of beta 3. Any question, friends, about difference and differences? In your exercise session, you will go through the code for estimating the same effects, and yeah, I hope you will understand how this works.
Ну, пока что вроде все
So-
понятно.
In
Yeah.
our case, we are not bothered with the high p-value of our estimate.
Well, we do. We always need to remember that statistical significance matters. And as I said, given this p-value of 0.13, we can conclude that the effect is not statistically significant. It is completely in line with our previous discussions. So the estimate is not statistically significant, so we cannot believe that this change led to the so the change in minimum wage led to the increase in employment. But again, we cannot conclude this before estimating the extended model with control variables. So I decided not to replicate the full construction of this estimation done by the authors. Of course, they introduced more variables, more control variables here. They found the statistically significant estimate of this effect. But in this case, my goal was to illustrate you the way how difference in differences is estimated. I didn't want to replicate the full study of these authors, and don't think that like it is enough to stop only with this simple baseline model. Of course, no. Of course, every paper extends this with some additional variables. So if you want, we can spend several minutes on observing the results of their study with the additional control variables. So here, that's basically what we have calculated with you. Look, average employment before, average employment after. So these numbers are replicated with us. This is the difference. In New Jersey, the same 2044, not able to find it here. So there are different groups of employment, so probably it was not every, yeah, here 2117, 2103. You see that they built many other things additionally here, and when they, yeah, look, they add control variables, a lot of control variables here. So of course, as I said, this baseline model is not enough to estimate everything. Much more. So where's the estimate? Basically, we can look at this table. Look, they also control for the chain and ownership, because the data is available also for the different brands of these fast food restaurants. And so if they introduce it here, so you see that the estimate slightly changes. And they also use another independent variable as the initial wage gap, right? So the wage gap reduces when they control for additional variables. So if you want, the paper is available for free. You can go there, read, and study this better. So overall, of course, statistical significance matters. Don't forget about this. In the baseline model, this statistical significance is not shown. So the second special technique that we will discuss, very popular, very fashionable, and so the econometricians started using this since the beginning of 2000s. So if you would be lucky to find the appropriate setting for using this regression discontinuity design, well, you might become very famous econometrician. So what is specific? So regression discontinuity is not possible to apply everywhere. So difference in differences is more applicable in the usual studies. Regression discontinuity is very specific, but it's very interesting. So when regression discontinuity can be applied, when there is some specific situation, when receipt of the treatment depends on some observable variable W and depends on the fact that this observable variable crosses a given threshold value. So the observable variable W must be continuous. There must be some threshold, and if this observable variable exceeds the threshold, then a person or firm receives a treatment. If this observable variable does not exceed a threshold, then individual or firm does not receive a treatment. So for example, when this occurs, we can make a study about the political incumbents and do they have an advantage in elections. So who are the political incumbents? Incumbents are the winners of the previous election. So a person who already possesses some position, like, I don't know, the current president, the current prime minister, the current head of government, something like this. So, and then the next election happens, and we want to know whether this person who already has this position, whether this person has some advantage in elections. How can we study this effect? Of course, if we simply compare the votes for incumbents and the challengers, well, probably it is going to be highly biased estimate and well, not reliable. But we know that there is an observable variable, the vote share, right? Because you win if your vote share is, so if you received the maximum share of votes. And it means that it must exceed a given threshold. So sometimes if there is, I don't know, in some countries you must exceed 50% plus one vote. In some other countries you must get just a majority of votes. Still, there is some given threshold that you need to exceed. And if you exceed, you receive a treatment. In this case, the treatment is that you are becoming incumbent. So the treatment, incumbency, depends on the fact whether observed variable vote share exceeds the threshold. Well, in the previous election, of course. Or another example, what is the effect of college attendance on your future income, for example? So the college students are admitted based on the admission exam. And in order to be admitted, you need to exceed some specific threshold. So, for example, a college takes only applicants with the only 200 applicants with the maximum exam score. Then there is a threshold that divides 200th person and 201st person who is not admitted. So these are treated, these are not treated. So the treatment depends on whether the observable variable, in this case exam score, exceeds the threshold. You see that this is a very specific case. There must be some variable, there must be some decision rule in the form of threshold, and everything that is beyond the threshold is treated, is given this treatment, and everything that is before this treatment, before the threshold, are not treated. So, and what is the most important thing in this regression discontinuity design? Near the threshold, the treatment can be viewed as randomly assigned. Well, because if you are taking the first or second person in the rating for the college admission, of course you can think that, well, these people are very smart and they are very different in their unobservable characteristics from people who do not who did not pass the exam and who are not attended to the college. But if you compare people near this threshold, like 5 people, 5 last people in the rating who are admitted, and 5 first people who are not admitted. So probably the difference in their scores is going to be very small, and probably the difference between their individual characteristics is not also large. So maybe their brains are similar, maybe their abilities are similar, and all the other characteristics are similar. But one part of these people is in the treated group, they receive the treatment, and another part of these people is in the control group. Remember, when we spoke about randomized control experiments, again, we wanted both groups to be as similar as possible, and only one difference must be between them: the difference in treatment. And in our case, those who are very close to the threshold, but some passed and some did not pass, they also might be similar. And this setting is called the regression discontinuity design. Why discontinuity? Well, because around at the threshold, this discontinuity occurs. Some people receive treatment, some people do not receive treatment. This is an illustration of what we are talking about. Look, what was the example of Stock and Watson? Well, their example was the following. Suppose that students are required to attend summer school if their end of year grade point average falls below a threshold. So basically, if the students are not performing good during the year, then they are required to go to the summer school. Why? Because they need to improve their performance in the next year. And that's what we want to know. We want to understand if this policy, if attending the summer school, has a positive effect on the future outcomes of these students. Of course, if we look at the scatter plot, we see this abrupt change. These are people with the low grade, so those people who perform bad. And on the vertical axis, their score in the next year. Look, those who performed bad in this semester and they have been sent to the summer school, their results, well, for example, if your average was 1 this year and you attended summer school, your average is going to be around 2 next year. So there is some improvement, right? And so on. But now the question is, if we compute the average of these people and compare it with the average of these people, if you take the full group of people here and full group of people here, so the average here is going to be something like 2.5 around here, and the average here is going to be, well, almost the same, right? So maybe also 2.5, 2.6, something like this. It is not correct to compare people from this part of our group because they are really smart and their score is 4, so therefore they are not comparable with these people on the other extreme of our distribution. But people who are here are comparable because these people are just avoided of being at this summer school. They passed, so they exceeded the threshold. And for example, this person, this point, was very, very close to being in the summer school. But his or her average grade is slightly more than 2. Therefore, this person nearly avoided. And these also people, and probably these. And if you look at their average is going to be something like 2, right? So if you look at these points in the middle, there is going to be something like 2. But these people are less lucky. So these people were less lucky because their GPA was less than 2. They have been sent to the summer school. And in the next year, look what happens. The average for this cohort, the cohort which is very close to the border, to the threshold, is something like 2.6, which is higher than 2. And this can be thought as a causal effect. So we compare sample average near the threshold for the treated group with the sample average near the threshold for the control group. And this vertical distance is going to be the estimate of the causal effect. Now, probably the outcome can be something else, like if the student drops or future earnings, something like that. So that is why you will see, so yes, in this case, it's going to be something like 2.5 minus 2. But if you compare the full sample average of this group and this group, as we have discussed last lecture, which is the difference estimator, you will not get anything reasonable. Well, there are 2 types of RDD. In this case, you also may ask, well, if this is obligatory for the person to go to the summer school, what if some of these people would not go? What if some of these people would ask to go to the summer school? If this is the rule, like strict rule, or if there is something like the decision. Remember, we spoke about following the treatment protocol in the randomized control experiment. So the same situation may occur here. So, and with this regard, we kind of introduce 2 types of RDD. So one is called sharp RDD, when there is a sharp threshold and everyone who is below the threshold is maybe treated, maybe not treated, but there is no possibility to kind of decide which group you want to choose. and everything that is on the other side of the threshold is, for example, not treated. And fuzzy RDD. So fuzzy RDD is more realistic because people can decide. People can choose. As I said, if you are sent to the summer school, you can skip for some reasons. Or if you are not obliged to go to the summer school, you can ask attending it. Well, in the sharp RDD, the receipt of treatment is entirely determined by our variable W. In fuzzy RDD, so crossing the threshold influences this receipt of treatment, but not fully. And as we discussed about non-compliance in the randomized control experiments, we can use here instrumental variables. I'm not going to go there and discuss the techniques, but if you, in your future career, if you would ever wanted to use RDD for your specific cases, so remember that the problems with fuzzy RDD might be solved with the help of instrumental variables. As an instrument, we would use the binary variable that this W exceeds the threshold. So basically the prescribed treatment as in the randomized experiment. So how should we estimate the effect of regression discontinuity? You see that it is not that simple because we are not going to compute the full sample average for treated and control group. So first and most important thing is to set this window around the threshold. So how wide is going to be this window in which the observation fall? So it is called bandwidth. So the size of this band that includes the units under study. And then it's simple. You simply need to compute the average here and here. But if we want to translate this in the form of OLS, then something following can be applied. I want to warn you that this is a very simple case of RDD. In the real studies, people use more extended versions, non-parametric estimations of the functions. So I'm going to just demonstrate you the most simple case when, again, there are just two dummy variables. So let us introduce the dummy variable x equals 1 for the treated individuals and 0 otherwise. And let w be some observable variable, continuous variable, it is not binary, and c is some threshold. Then treatment x1 or 0 depends on this variable. This variable is called the running variable, and c is sometimes called the cutoff. So in sharp RDD, x1 is 1, xi is 1 if w exceeds the threshold, or less than threshold, depends. And x is 0 otherwise, only if w is less than the threshold. So this is not a rule. You can switch them. You can switch 1 and 0 here and here. It's up to you. Because in the illustration, we had the other case, right? So we had the case when x is 1 if w does not exceed the threshold, and x is 0 otherwise. And then the estimation procedure is the following. So first of all, we regress the outcome variable on this running variable, w. Then here happens something interesting. Look what happens. Running variable minus the threshold multiplied by x. X is the dummy variable. And then beta 3 multiplied by x. So let's try to think what is going on here. If x is 0, then y is a linear regression model here, this one. I guess it's simple. So for the control group, we have this. Let's go back here. It's gonna be this part. Just a regression line. What happens with the treated group? If x is 1, then the intercept instead of beta 0 becomes beta 0 plus beta 3. So this is exactly by how much your intercept is gonna differ between treatment and control group. So what happens here? Beta 2 times x, x is 1, and times w. So the slope changes from beta 1 to beta 1 plus beta 2. Okay, so we control for different slope, potentially. Why this minus c is necessary here? Look, beta 2 times c is the part of a threshold. Sorry, the part of intercept. So therefore, the intercept is going to be beta 0 plus beta 3 minus beta 2 times c. Please, just to make this line slightly below, like here. You need to shift this line to the left to compare the intercept here with the intercept here, right? So that's why you want to shift all this part beyond the threshold to the left. That's why you subtract c. That's why you do this. There are some other methods to do the same. So I have chosen the most simple and the most understandable. And as an illustration of this regression discontinuity design, I want to show you this following study. Ludwig and Miller, does Head Start improve children's life chances? Evidence from regression discontinuity design. So what is this about? There is a program in the United States called Head Start. It was established in 1965, and they provide, with this program, they provide preschool, health, and other social services to poor children, aged 3 to 5, and their families. The idea of this program was the following. So in the spring 1965, the federal government in the United States has chosen 300 poorest counties in the United States, so small municipalities. 300 poorest. So which means that we need to select 300 counties based on some variable. And there is going to be a threshold that divides 300 poorest from the rest of the counties. And these 300 poorest have been selected based on the poverty rate, computed into 1960, I guess. And these counties received a large exogenous increase in funding. Why? Because initially they were the poorest, and then the federal government decided to help them. It is based on the observable variable poverty rate. Of course, the most poor counties are not comparable directly with the richest counties. It is not possible. But again, around the threshold, for example, the 300th county with 301st county, they are very comparable because probably the poverty rate is not that different for them. But one county receives treatment and the other one does not. So for the illustration, let's y be the mortality for children in the age between 5 and 9 years. W is the poverty rate in 1960, and so I follow the author's construction. So the cutoff is 59.9084. Why? Because this is exactly the threshold between 300 poorest counties and the rest of the counties. And the authors took the observations around this cutoff and they took the window of 8. So basically, they selected only the counties plus minus 8 to the cutoff. Exactly as I explained you on this picture, that we are not taking the full sample of these points, but we concentrate on the subsample of points around the cutoff. And the width of this window is 8. So here is the result. Well, let us see the estimated regression line. So what is interesting for us is this estimate of this coefficient minus 220, which is the estimate of the causal effect of this program on the children mortality rate, and this result is statistically significant. It is less than 5%. So which means for us that participation in this program reduced the mortality rate by 2.2. Frankly, I don't remember what was the initial, so just to compare whether it's kind of economically significant or not. Probably yes. So you will discuss this during the exercise session, I guess, because we are running out of time. So you will compare this effect, which is statistically significant, with the overall mortality rate of kids in these poorest counties, and you will conclude whether this is economically significant, whether it is reasonable estimate or not. And I believe this is all. So we covered 2 popular techniques for the estimation of the causal effects. And with this, we finish the part of cross-sectional econometrics. And in the next part, after the midterm, we will start discussing the time series econometrics. I expect 6 lectures there. So I hope that we will be able to cover something interesting. So the plan for the future. Quiz number 5, I guess. It's not 4. Yeah, must be 5. Based on the recent lectures, it's going to be available from tomorrow's midnight till Wednesday midnight. Home assignment number 5. Simple estimation of difference and differences and regression discontinuity. Be careful. It is available until Sunday midnight. You may ask me why, because on Monday you will have a midterm. Just before talking about the midterm, let me explain one thing. So I included this topic into the course only this year. And I'm not sure whether I'm gonna be able to prepare for you some self-study based on differences and regression discontinuity. Therefore, I'm not showing it here. So if I have time, I try my best to provide you with self-study. But if not, then you need to do this home assignment without any kind of training, but only the exercise session. So in the exercise session, you will discuss the code, the estimation procedure, and all the necessary steps. And the home assignment is not going to be difficult. Don't panic. So therefore, well, wait till the end of the week. If the self-study appears, then good for you. If not, then proceed with the home assignment without any preparation. Because I know I spoiled you with the self-studies, probably. So the midterm, what to expect? Multiple choice questions, calculated questions, estimation exercise, based on one of the covered topics. So we have covered panel data, we have covered binary dependent variables, we have covered instrumental variables, and these two techniques, difference and differences, and RDD. Well, to make your life slightly simple, I would not include this into the estimation exercise. It would appear, of course, it will appear in one of these tasks, but not in the estimation. So for the estimation, you need to remember only 4 home assignments that we've made: binary dependent variables, panel data, instrumental variables. What is else? What's the last? I forgot. Panel data. Yeah, so the first one is about the review. Okay, so then panel data, binary dependent variable, instrumental variables. So 3 possible tasks, 3 possible topics that can appear in the estimation exercise. And open questions. Of course, open questions are going to be related to the estimation exercise. Please explain what have you computed. Please provide some judgment whether the estimated effect is statistically significant, economically significant, what does this mean, and so on. So these 2 are going to be related to each other. Questions?
I have a question regarding this threshold. Like, we pick the treatment group as the first is 300 counties. And the control group, does it, like, I didn't catch this threshold. Like, we pick control group out of the border of 300. Like, we pick 300, first 300 treatment, and for example, next 300 is the control. Or
no,
they
look,
also include
the treatment and control group in regression discontinuity is not the whole part of those who are treated and those who are not treated. The main idea here that when you talk about treatment and when you talk about control group, you need to concentrate on these closest observations to the threshold. So those who are here, you can call them as treated group, and those who are here, you can call them as the control group. So of course, all these observations are under the treatment, but you cannot compare these observations with these observations. It is not reasonable. So that's why when you speak about treatment and control group, it is better to only take these ones. So therefore, when we in this empirical exercise, not all 300 observations are used in the estimation. We take some part closest to this threshold from one side, those who received this funding under the program, and some part also close to this threshold who do not receive the funding. So you see that overall there are 482 observations. So some of these 482 observations are coming from the treatment group, and some of them are coming from the control group. Frankly, I don't know how many counties are from one part and from the other part. I believe I will include this in the code, and you will look at this closer in the exercise session. So everything that I can show you is at the moment is this, but this is not very illustrative, right? Because you see that there is no kind of visible discontinuity in this case, right? So the left is the count is with below the threshold, so those who are not treated because their poverty rate is less than 59. And these orange dots are those who are treated. And you see that, well, some number of, it's not 300 here, it's less. And of course, it's not all the other counties here. Those only who are very close to this border. Because look, if I build the same for the whole data, you will see something like this. Look, this is nice. The whole data, and the poverty rate differs from, I guess, 0 to almost 80%. But we concentrate only on this sample of counties who are very close to the border between treated and not treated counties. And this is, well, yes, this is somehow like, how to say, subjective. So how wide must be this window? We can make it like 8, as in the case of authors. We can make it like 10, 15. So how wide it must be? Usually in studies who are working with regression discontinuity, there are several thresholds. There are several bandwidths, sorry. These distances from the threshold. So they take like 5, 10, 15, 20. And if the causal effect does not change severely, then you can claim that, well, you see that even if we expand the bandwidth, our estimate doesn't change. So the estimate can be trustful, I would say. There are some kind of rules of thumb in the books how to come up with the optimal bandwidth, but there is no some formal rule how you need to choose it. Just, you can look at your data and choose the most appropriate.
And also, do they have to be equal, like the
not necessarily, but at least somehow comparable. It's not like 2 here and 100 here. It's better to have more or less homogeneous groups from one and from the other side, but not necessarily to have like 200 here and 200 here. No, you may have like 150 here. And okay, so since we have started this discussion, let me see how many are there. So sample treatment. Yeah, so not treated 279 and treated 203. So almost equal. So 279 whose poverty rate below 59% and 203 whose poverty rate is above. But if we look at the whole data, you see there are 2,489 and less than 300. Well, basically, not all counties are treated here. 194. And a nice function from Python, value counts. If you need to compute how many distinct values in your variable present. Anything else we need to discuss?
I guess no. wanted to ask about this line of the code, but I guess we'll cover it during the exercise.
You mean this?
I mean sample this more.
You will go through the code, and yeah, this is gonna be left to the exercise session. Don't worry. Okay, friends, I need to finish. Thanks for your participation. Good luck with the midterm. If there are some questions during the preparation, let me know. Otherwise, as usual, the midterm is going to be available on the course page. Read the task carefully. I will be online during this time just to control that you accessed the midterm and everything works in the correct way. And by the midterm, I hope I will be able to go through all your home assignments, quizzes, because some quizzes are needed to be graded manually. So you will have some preliminary results before the midterm based on your home assignments. Have a nice week, have a nice evening, and see you on November 7th, I guess.
Thank you.
Bye-bye.
Thank you for the class.
Wish us luck on the midterm.